All right. Hello everyone, and welcome to a few central force examples, water in a bucket. Now, you probably saw in class a little demo that I did where I spun some water around in a bucket on the end of a string. And so I kind of want to analyze this a little more fully here. This is an example of moving in a circle at constant speed in a vertical circle. As you're going to see, that makes things a little more complex. Okay? So, let's start out by doing some force diagrams of the water bottle. And in particular, I want to do those force diagrams at kind of the extreme points, which would be the top and the bottom of the circle. Let's start out at the top. Okay. What forces act on the water bottle at the top of the circle? Well, of course, gravity acts on the water bottle, and that would, of course, act down. Now, the water bottle is also interacting with the can, right? There's a normal force there. Now, if you watched yesterday, you'll notice that the can is upside down at the top. Right? So therefore, the water bottle's upside down, and the normal force will act down, because it's underneath the can, if you will. Now, the size of that normal force will really depend on how fast we spin it. The harder I pull on the string, the more the can will push on the water bottle, the bigger the normal force will be, the faster it'll go. So let's say that I spin it in a way such that the normal force happens to be twice as big as gravity. It could be smaller than gravity, it could be the same size as gravity, it could be way bigger than gravity. It really just depends on what speed I spin it at. So let's say I spin it so that the normal force, which is acting down, is twice as large as gravity. Then the net force acting on the water bottle is, of course, the vector sum of those two forces. The vector sum would be negative f of g minus f of n. Why are they both negative? Because they're pointing down. Right? Down is negative. And if f of n is actually 2f of g, then the net force acting on the water bottle at the top of the circle is roughly negative 3f of g. And the net force acting on the water bottle is the centripetal force, the net inward directed force. Notice it's inward. Down is inward in this case at the top, which is making it move in a circle at a constant speed. Well, let's look then at what's going to happen at the bottom of the circle. Well, at the bottom of the circle, the force of gravity still acts on the water bottle. And in fact, the same force of gravity works on the water bottle because the mass of the water bottle hasn't changed, right? It still weighs the same amount. So, same length force of gravity arrow. But now at the bottom, the bottle and the can are right side up. So instead of pushing down on the bottle, the can is going to push up on the bottle. Right? I'll pull up on the string will pull up on the can will push up on the bottle. So the normal force here will be up. But how big does that normal force need to be? Well, first of all, consider that since the water bottle is moving in a circle at constant speed, the net force, or centripetal force if you will, acting on the water bottle is equal to, as we found in the lab, mass times speed squared times radius. And since all three of those things are constant, the net force has to be constant. Which means the size of the net force here has to be the same as the size of the net force there. Which means the net force at the bottom has got to be 3f of g. Now in this case though, that's 3f of g upward. Because inward at the bottom of the circle is up, right? And the net force always has to act inward to make something move in a circle at a constant speed. So, if we want a net inward force of positive 3f of g, and f of g here is pointing down, how big does the normal force need to be? Stop and think about that for a while. Welcome back. Hopefully you said the normal force needs to be 4f of g's. Why? Well, the net force would be f of n minus f of g. F of n is up, so it's positive. F of g is down, so it's negative, so we have to subtract the two. And if f of n is 4f of g, 4f of g minus f of g, that's right, it's 3f of g, the same centripetal force that we have at the top. So notice here, I've got to pull on that string a lot harder at the bottom than I do at the top. And so actually, to make something move in a circle, in a vertical circle, at a constant speed, is not that easy of a thing to do. You actually have to change your force constantly as it goes. It's the smallest at the top, it's the biggest at the bottom, but in between, it's in between. Right? So you're going to have to constantly vary the force that you're pulling with so that you have the same net force so that it will move at the same speed. Kind of interesting. But notice here, at the top, that normal force is smallest. At the bottom, that normal force is biggest. Why? Well, it's got to do with the direction of the force of gravity. At the highest point, the force of gravity is pointing inward, down. And so the force of gravity is helping create that net centripetal force that we need to keep it moving in a circle. At the bottom, however, that force of gravity is pointing out of the circle. So that means if we need a net inward force, we have to first overcome that force of gravity and then provide the same net inward force. Right? So as you see here, we had to put a lot more force on here. So gravity's helping, gravity's working against us down at the bottom. Okay, let's do a couple of examples now. The first one, what is the fastest speed at which the can-water combo, notice not the water this time, but the can and the water total, could be spun without breaking the string? That's if the can in the water has a mass of 0.362 kilograms, the string is about 0.70 meters long, and the test of the string is a 100-pound test, which is 445 newtons if you convert. If you don't know what test is the rating of how strong the string is. It's how much force you can put on it before it'll break. If you go to like a Home Depot wall O string, the strings are all going to be rated by test. If you've ever been fishing, that's how you rate fishing line, right? Depending on what kind of fish you're going to do, how strong the string is, or the fishing line is, sorry. So in this case, this is a 100-pound test that I was using, which means I can put about 445 newtons on before it'll break. So, first question. Before we actually do all this, let's go ahead and do a motion map of the can and the water. Okay? Motion maps consist of dots for position, velocity arrows, and acceleration arrows. Now, you might notice here I did only the bottom half of the circle. Why? Well, look at the question. We want to know the fastest speed before we break the string. Well, where is the string most likely to break? Look at our previous thing, right? It would be at the bottom, because at the bottom you've got to balance out gravity and then provide the net force. So that's why I'm only going to do the bottom part, because the bottom is really where we're going to look. That's where the string's most likely to break. So, first of all, it's moving at a constant speed. So what should be true about the placement of my dots? That's right, they should be equidistant from one another. Make sure, by the way, one of your dots is dead at the bottom so that it's the point we're going to analyze later. So all of these should be the same distance along the arc apart. Now, constant speed means the velocity arrows should be the same length. However, the velocity itself is not constant. Remember that it is constantly changing direction. So what direction does the velocity act? Well, it's that special tangential velocity. So that means imagine a radius being drawn from the center to our point, and then draw your velocity arrows tangent to the circle and draw them the same length. So the next one would be here at the bottom. It would go directly to the left, and up a little, and then up a little. Now notice here these velocity arrows are turning as we go from point to point, and they're kind of turning inward. That's because the acceleration is acting inward. And since it's a constant speed, the acceleration is constant, and therefore the arrows, acceleration arrows, will be the same length, but always pointing inward towards the center. So there's the acceleration. There's the acceleration. At the bottom, the acceleration is upward, inward, inward. So there's our motion map. If you draw a couple of these, you're going to hopefully get locked in your head here the directions of the velocity and the acceleration for uniform circular motion. Okay, now let's draw a force diagram of the can-water combo at the bottom of the arc. So right here. What forces act on the can and the water? Well, of course, gravity acts, and gravity, as always, acts down. Also, the can is interacting with the string, so there'll be a force of tension. And at this point, that force of tension would act upward because it's at the bottom. Now, question is, how big would that force of tension be compared to the force of gravity? My supposition is that it would be bigger than the force of gravity. Why? What direction is it accelerating? Inward, which is upward. And if it's accelerating upward, what direction does the net force have to be? That's right, upward. And for the net force to be upward, the force of tension must be larger than the force of gravity. So it all ties into what's going on, right? So you got to think through that here to decide how big these forces have to be relative to one another. Now that we have the force diagram, let's analyze it and try to figure out the fastest speed it can go. First of all, the net vertical force is equal to mass times acceleration. That's Newton's second law. It is accelerating upward. So the net vertical force is the tension minus gravity. Notice I took the arrows off of them because I put in the directions. Tension is up, positive. Gravity is down, negative. And notice I also took the arrow off of the acceleration. The acceleration, as we talked about, is upward, so positive. So I got rid of all of the directions. Also, this is not just any acceleration. This is the centripetal acceleration. So, again, check this out. Make sure you understand why positive, centripetal. Now, a couple of things we know. We know, as we've done many, many times, that we can rewrite the force of gravity or weight of the water and can as the mass times the gravitational field strength. So that can be substituted in there. We also know after our lab and our proof that the centripetal acceleration is a special acceleration. It is always directed inward and has a magnitude of speed squared over the radius. So we can plug that in as well, giving us the force of tension minus the mass times the gravitational field strength equals mv squared over r. You notice how this is the net force, which is the centripetal force, which is the difference of the forces? This all fits together. Now, in order to get the maximum speed, I'm going to put in the maximum tension. In other words, the test of the string. Now, we have to solve for the speed here. Okay? I'm going to do a couple steps of algebra, but be careful. Some of you might be tempted to cancel the mass out because there's one here and there's one here. But there isn't a mass in this term. So don't be sloppy with your algebra. You can only cancel something out if it appears in every single term. So, first of all, I'm going to multiply by the radius, move that over here, divide by the mass, move that down here. And I'm going to flip sides because I like to have what I'm solving for on the left, reflexive property of equality. And then take the square root. It's not a pretty equation, but it's an equation that's certainly algebraically possible to find. Now we plug in the many, many numbers, and if you really want to have some fun, try to see if the units work out. And as long as you put everything in correctly in units of kilograms, meters, and newtons, right, those things have to work out to be the right units. You can't use grams or centimeters because you have newtons in here on the 9.8. You get an answer of 29 meters per second. That's like 70-something miles an hour. So more than likely I would rip my hand apart before I would even come close to breaking the string. So it's a nice, safe little demo apparatus.
Son, if you don't believe in me, believe in America. America, where any man can make quick money with no questions asked.
Get right up and win my trust. All you have to do is conquer the ball of death.
What's the catch?
No catch, just ride the motorcycle all the way around just one time. 3 tries for $10.
Arch, how much money do we have?
$10. Woohoo! That counts as a try. Ow! That's 2. Ow! And that's 3. Tell you what I'm going to do. Just because I like seeing you hurt yourself. I'll give you 1 on the house.
You're the best.
Dad, when you get to the top, don't slow down. Speed up.
But that's when it's the scariest.
Just do it.
I'll take that truck now.
Oh, man. My wives are gonna kill me.
Ah, The Simpsons. So let's analyze the ball of death here. I want to know what is the slowest speed, V-min, Homer could have and not fall off of the ball of death. Now I'm going to assume here that the ball of death is approximately 7.2 meters. That isn't just a number I pulled out of my head. I assumed Homer was an average-sized male and estimated, using the height of Homer, the diameter of the ball of death, and then calculated its radius. So I'm pretty confident that that's pretty close to what it was in that silly little movie you just watched. Now, where is Homer most likely to fall off of the ball of death? Of course, at the top. So let's very quickly here do a motion map of Homer as he drives along the top of the ball of death. As in the last one, if he's moving in essentially a constant speed as he goes around the loop, the position dots should be equidistant. Make sure there's one right at the very top. The velocity arrows will always point tangent and should be constant length because it's constant speed. So there's the velocity arrow. So at the highest point, moving to the right. And the acceleration arrows should also be constant since the speed and radius are constant, and should point inward. So at the top, the acceleration is down. And remember, that means the net force will be down. So there's our motion map. So we've really made a motion map of the entire circle with the last couple of problems. Now let's draw a force diagram of Homer at the top of the ball of death. Of course, gravity acts down. But there's also another force here, right? There's the force of the seat on Homer's rotund, blue-coated bottom. And since he's upside down at that point, the normal force will act down. Now, we're not really sure at this point how big that'll be. It'll kind of depend how fast he's going, so we'll talk about that in a minute. So hopefully you see why both of these would point down. Okay, now our special case is the slowest possible speed. So the question then is, what would the normal force be at the slowest speed? Well, think about this. The slower Homer goes, the smaller the normal force would be, right? Because Homer would press less against the seat, so the seat would press less against him. And if he goes too slow, he's going to fall off, and then he won't have any force, normal force at all. So the slowest speed is when that normal force shrinks to zero. Think about that for a second. You might remember me spinning the can in a circle, and when I did it so that the water almost fell out of the can, the string went slack. Right? I stopped pulling, essentially. So at the slowest speed, you don't need any help. Gravity is enough to keep you moving in that circle. So that means our force diagram is now just the force of gravity. And this becomes a relatively straightforward one to analyze. The net vertical force is ma, but there is only one force, F of g, which is down, which makes it negative. The acceleration is also down, so that makes that negative. Notice we got rid of both of the arrows. And it's moving in a circle at a constant speed, so this is not just any acceleration. This is the inward directed centripetal acceleration. And as we've done before, oh, by the way, at any speed faster than the minimum speed, this would be the equation. And you could solve this equation for anything, right? So this is just a special case where the normal force shrinks to zero, and if he goes any slower, he'd fall off. Of course, the negatives cancel. The force of gravity is our old friend mg. The centripetal acceleration we now know is speed squared over radius. Plug it in, and I'm going to call this v-min. And now notice the mass here and the mass here are the same. They're in both terms, so they cancel. It's kind of interesting. And that's because the more mass you have, the bigger your force of gravity is, the bigger the net centripetal force is. So there's more force trying to accelerate you. But if there's more mass, there's also more inertia, a greater tendency for you to try to go tangent to the circle. And those two things will cancel out. Now this is kind of nice because it really means that it didn't matter whether it was Homer or Bart driving the motorcycle, they'd have to be able to go the same speed. So if you're designing a roller coaster, say for example, it really doesn't matter theoretically, as long as you can neglect friction and things, whether that's full of people or there's only one person riding. It's all the same. Solve, multiply by r and take a square root, and there we go. Notice that the minimum speed is only dependent on the radius. The bigger the circle is, the faster you have to go, which should kind of make sense. You've got to go faster sideways, right, so that you don't fall off of the circle. And also, the bigger the gravitational field strength is, which of course is a constant here on Earth for the most part. But if you went to, say, Jupiter and tried to do this, you would have to also go faster because gravity would pull on you harder. Plug in our numbers, and we get an answer. About 8.4 meters per second. That's only about 20-some miles an hour. So it's possible he may be able to do this. Now this is an actual thing that they do at circuses, but a lot of times what they do is instead of starting from rest like Homer did, they actually drive around kind of the bottom a little bit, so they don't actually go all the way around, so they build their speed up, and then they turn and they get going kind of higher and higher, and then eventually they go up over the top, and then they can just zoom all over the place. Right, so they kind of build their speed up a little bit, which Homer didn't do. So it would probably be pretty hard for him to do the way he did, to accelerate that quickly, to get to 20 miles an hour in that short little distance. But, you know, it can be done if you kind of build up your speed. So I hope this helps you start to begin to see how we can do some things with constant speed in a circle. 19 miles an hour.